But let's go back to page 72. So did we start example 4D?
No.
We didn't even start it. Did we do C?
Yeah, we did C.
No, C would have been enough. I wish I would have known that.
Yeah.
C was enough to do D. I wish I would have looked up one more before I said that. Okay, so let's go over C again. It was the very last thing before we ran out of time. We'll go over C again, finish D, and then the quiz will be easy. So C was the 80th percentile. We had drawn this picture. And we had decided that the 80th percentile was roughly, I think we probably already did it. But we decided to draw it where, in general? Yes, on the left?
The one?
Near the 1?
Sorry, sorry, hold on.
We're looking for somewhere, some number that has 80%.
Yeah, we guessed at one.
We guessed around 1, but why did we guess here?
Because it shades about 80%.
Because we want to shade about 80% of the area. I think if I remember, our answer was more like here. But we wanted to shade some number, question mark, so that this area is 80% or 0.80. That's what we were looking for. And we did it 2 different ways, I think. We looked it up on the table and we used our calculators. Or did we just do the table? Anybody not have this with them today? I have extras. You want to bring it every single day. And we'll refer to it every day. There you go. So what we're really asking for is, what is this z-score right here? Because these are the z's on this axis. We know the probability, but we don't know the z. So how did we use our table to find that? We look for the number closest to 0.80. We're working on pages 5 and 6, 4 and 5. Sorry, 4 and 5. Which page do I want to look on? 4 or 5?
5.
Why 5? Because we know it's a positive z-score. Based on our guess, we know it's some positive z-score. So we're looking on page 5. And we know the probability. Where are the probabilities on this table? Where are they?
In the middle.
In the middle. The middle are the probabilities. What's on the edges?
Z-score.
The z-scores. So we're looking in the middle for the probability closest to 0.80. The probability closest to 0.80. We had this discussion last time, I remember that.
Mm-hmm.
Is 0.7995. I just wrote 0.80 as a 4-digit number, but same thing, right? So we searched through there, we found the 7995, which correspond to a z of 0.84. Looking on the left edges to get the z that goes with it. So once you find that 7995, I have to point it and turn around again. I lost it again. There it is. Once you find the 7995 in the middle here, then you're going to look over to the edges to see what that z is that goes with it. Yes, ma'am.
How do you know when you look in this and when you look on the left side? How do you remember?
Good question. She says, how do you know when you look on the edge compared to when you look in the middle? When you know what z is, it even says here that z are the numbers on your left. Just a z in that column. If you know what z is, you look up your z to find the probability. In this case, we didn't know what the z was. That was the whole question. What is the z? So we can't look on the left because we don't know what number it is. But we do know we have the area, and what's the area represent? Probability. Remember the big picture was, remember the area equals probability. So it depends on what you have and what you're looking for. In this case, we don't know what z is, but we have the probability, so we look in the middle and work out to the edges. Other questions? Okay. Did we talk about how to use our calculator to do this one? Inverse norm. So aside from the table, our other option is to get inverse norm, which is still under distributions over there on the right where it says vars. Right by the same place you find normal CDF. When you do inverse norm, you have to tell it the area to the left, the the mean and the standard deviation. Did everyone find the inverse norm function on your calculator? If not, ask your neighbor or me to help you find it. Inverse, I think of it as reverse. I'm working in reverse. I don't know the z's, I'm working in reverse. So in this particular problem, what am I going to put in here? 0.80. 0
and 1.
And 1. Because we're working with standard normal, the mean was 0, standard deviation was 1. What does that give you? 0.84 and some change, but if we round it off to 2 decimal places, do we agree we got the same z? So just like probabilities, you can either use the table or the calculator to find probabilities or to find z's. This was C. Remember that one now? Been a while since Wednesday? Okay, so let's do D. Let's do D. What temperatures separate the bottom 10% and the top 10%? So again, we're dealing with these thermometers. What do I mean by the bottom 10%?
On each side on the ends, right?
Well, so it says bottom and top, but just the bottom, so he's saying 10% on both sides. The bottom 10% is where in this picture? What did you say, Kirsty?
Tail.
Which tail is the question? Where am I going to guess for bottom 10%?
Oh, you the left.
Somewhere to the left, somewhere, I don't know, over here? Where this area on this side is 0.10? Why is that the bottom? That's the hardest part, so we'll be like, what'd you say, Brian?
Negative.
Yeah, it's negative. These are the smaller numbers, these are the bigger numbers, so these are the lower end, these are the upper end, the bottom, the top. Think of your number line, okay? So, does this picture look pretty similar to that one we just did?
Yeah.
Almost identical, just a smaller area now, right? Again, we're looking for the z-score. We're saying z equals what right there? What z cuts off exactly 10%? So let's just use our calculators this time. How do we do that on our calculator?
Inverse norm.
Inverse norm.
And would it be 0.10
Yes.
and then 0 and 1?
0.10, 0, and 1. The area to the left, the 0, and the 1, because that was our mean and our standard deviation. And what do we get? Negative 1.28? Someone agree with her?
Yeah.
What's that tell you about my picture?
That it should be shaded at negative 1.2.
Yeah, I guessed a little bit too far to the left. Negative 1.28 is a little bit closer to the 1. So maybe it's more like over here somewhere. But again, if you're just guessing, I'm not going to mark you wrong for having your guess in the wrong place. But the idea is that you can tell your answer should be negative because it's on the left. To have some idea what the answer, if it makes sense. So our guess was fairly close. So 10% of the thermometers have temperatures below negative 1.28. And then the other part was the positive side. So I'm looking for this side. The top 10% is everything over here. Now there's two ways to get this one. There's a quick and easy way, and then there's the use our calculator again, which is still quick and easy, just not as quick and easy. Yes?
Couldn't we just use the positive since it's the same percentage away?
Perfect.
So it'd be
That's the
positive.
quick and easy way. If this number is 10% at negative 1.28, do you agree with her that positive 1.28 should be the same over there because it's perfectly balanced? So one quick and easy way is to say this must be z equals positive 1.28. because they have to be balanced. If the tail on the left is 10%, the tail on the right should be the same side. That only works because you have 0 in the middle. We'll talk about it a little bit later, what if 0 is not in the middle. But let's say I didn't notice that. I hadn't paid attention. And I wanted to use my calculator to find that one right there. What would I put into my calculator to find this one on the right?
Point 90.
0.90, he says. Why 90?
Because it's everything left.
Because you have to put in the area to the left. Beautiful. If we want 10% to the right, we have to tell our calculator everything to the left of that. And if there's 10% on the right, there's 90% on the left. So you could have done inverse norm of 0.90, and you should get the same answer. They're both quick and easy if you ask me. But. Questions? Think we got those? Quiz question should be easier now. Because right here, when I asked for 10% on the bottom, what's another way of writing that with percentiles? What percentile?
10%?
10%, so we could have said find P10. Find P10 is the same as find the cutoff that has 10% lower than it. Just another way of saying that. So that was one of the quizzes where it said find P5, I think. We good? Okay, so let's talk about critical values. Has fancy words, fancy name. The good news is the same thing we've been doing. Look at what it says, a critical value. Oh, yes, ma'am.
How did you find the Z's?
This one or this one?
That one.
Inverse norm.
Okay. And then where did you get the 0.90?
Because if there's 10% to the right,
Oh, okay.
there's 90% to the left. That's the big thing, is you always tell it the area to the left, even if you're talking about the right.
Okay.
So right there near the bottom of page 72, a critical value is a z-score that separates things that are likely from unlikely, just like we've been talking about before. And then they call this z with a little alpha underneath it, that little thing underneath there in the definition. That's an alpha. Theirs is fatter than mine. They're rounder than mine. That's a little lowercase alpha, a Greek letter. It's the z-score with an area of alpha to its right. Z-score with area of alpha to the right. That's the definition of a critical value. So our first example there looks like this. Z with a little 0.01 down there. What are they telling me to find? Just don't know what you think about that. What do they want me to find? So Kirsty just replaced the word alpha with the 0.01. She says find the z-score with an area of 0.01 to the right. Right? Because the number down here is the alpha. You see that? Find the z-score with an area of 0.01 to the right.
It's basically just shorthand.
Yes, it's shorthand for what we just did. Where do I draw the picture? Where's my guess for the z-score?
Right next to the one, so it's going to be close to 0.
Close to 0? I want the area to the right to be 0.01, which is 1%.
Right next to the
Close
3.
to 3.
Close to 3, maybe?
Yeah.
After 23.
After 3? Before?
Before.
Right before 3, he says? Maybe he's already done it.
I don't know.
We don't know for sure, we're guessing. Around 3 is what you guys are telling me though. Why is it around 3? Let's say it's here. Why is it roughly there?
Oh, because when you think about it as percentages, it's telling you positive,
Mhm.
and then so it would be closer to the 100, so it'd be like 1% away from being the end. of-
Right, 1% from the end, she kind of said. Or this area to the right here, this little tiny sliver, we call it a tail. What's the area inside there?
0.01.
0.01, yes ma'am.
So the numbers on the bottom don't really not correlate to the.
They don't, well, they're directly related to the percent.
Yeah.
Because we're asked what the question's asking.
Uh-huh.
But the percent is what percent of the area.
Oh, okay.
And then the question is, what number on the number line cuts off exactly that percent? So they are related. The area in here is 0.01. That's what this notation says. Find some z, it has to be way out here because we just want a little tiny little sliver, 1% of the area. We all see why it has to be way over here? How am I going to find that?
You do inverse norm, but then you put 1 minus, and then 0.010.
So she wants to actually type in 1 minus, which will work. I just want to talk about what's the area to the left. 99, and there's 1% to the right. Do we agree there's 0.99 to the left? Type it in 1 minus, will give you the same thing. 1% to the right. Why do I care about the left? That's what the calculator wants. The calculator always wants to talk about the left. So I'm going to type in 0.99 and my mean and my standard deviation. And what do we get? 2.82?
2.32.
2.33? Oh, I heard two different answers.
Yeah, he wrote it, so it's 2.33.
I thought I heard 83. Maybe I didn't hear the 8. 2.33?
Yeah.
Move around, yeah.
Anybody want to know where that number came from? Let's tell you about my picture. That was my guess. It's fairly close. 2.3 is maybe over here a little bit more. Your picture does not have to be perfect, but you should at least have some idea where your answer should be, because if my answer came out to be negative 0.5, negative 0.5 is over here. I would be worried. That's not nowhere close to 1% to the right. So you need to have some idea what your answer should look like. So this is my, oops, I changed colors on you. This is my z of 0.01. It's the critical value that goes with 1% to the right. Ask me a question because I'm about to have you do the next one without me. No question? Okay, try the other one. What is it? Z of 0.05? Z of something. Z of 0.05. First off, what does this mean? Z of 0.05 in words.
5%.
5%?
You want the area below?
5% is not the area below. It's to the right. Is that what you said?
Yeah.
Or Brian, somebody back there said it. It's always to the right. So I want 5% to the right. So again, I have to be over here somewhere. Not as far out where the 1% number was. So I don't know, maybe I'll guess over here. And we want this area to be 5% now, not 1%. So what do I need to know to use my calculator? I need to know everything to the left, which someone over there just said 0.95. 0.95 on this side. Hopefully you did inverse norm. 0.95, 0, and 1.
Yep.
What'd you get?
1.64.
1.64? Agreed? My picture was pretty good that time. How could we have done those last two problems with our table? What would have been different if I wanted to do either of those last two problems with my table? Yes, Ariana.
Like for the point, 05, we would look for the number that's closest to 5%.
We would look for the number closest on the chart, but actually we have to be a little bit more specific. Because even the chart talks about the area to the left.
And then subtract.
So would it be 0.95?
So we would have to be searching for 0.95 in our chart. Same reasoning, because the chart, remember I had you guys shade it last time and everything? So we would be looking for the number closest to 0.9500 in our chart. And if you go looking for that, you're going to find 1.64. And over here, we'd be looking for the number closest to 0.999900 in the chart, in the middle, and then looking on the edges for the z. So you're right, we gotta always make sure, remember, it's still the area to the left. Either the table or your calculator care about the area to the left. Questions? All right. So let's move on then and talk about what if it's not standard normal? What if you have a different mean and standard deviation? Let's flip over to page 76. Page 76. I have a little reminder up there of the z-score formula we saw way back when in chapter 3, I think it was. Remember that formula to find the z-score? A long time ago, where you could take some number minus the mean divided by the standard deviation. We're going to use that here in a minute, so that's why I'm reminding you of that. And then it says at the top in bold, if we convert values to z-scores, then the procedure for any normal distribution is the same as the standard normal. Notice that in example 1 there, I have 2 pictures for every problem. I'm going to show you why I have 2 pictures for every problem. So jumping in with example 1, we have adult IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. So if I want to label that picture on the left, for example 1A, I just want to label it, I don't even care about the question yet. I think reuse my picture here. What goes in the middle?
100.
100, because it's the mean, right? It's changing now. 100 is the mean. And what am I counting by now?
15.
I'm counting by 15. Because we were given that the mean was 100 and the standard deviation was 15. So we no longer are doing standard normal, we're doing normal, but now we're talking about IQ scores, and the average IQ score is not 0. So we can label this. This would be 115, 130, 145, adding and subtracting 15, 85, 70, 55, thank you for subtracting in my head. Okay with the picture? Always the mean and counting by the standard deviations. So the question in part A says find the probability that a randomly selected adult has an IQ score less than 120. Less than 120. How would I draw that on here?
Find it on the number line sheet.
Find 120 on my number line, so that's roughly right here. Here's 120. And less than is everything to the left. So I want to know what this area is. This area is the probability. Remember we talked about that last time. The area is the probability. Problem is, I can't look up 120 on my table. Why not? I couldn't hear what you said. Was that you, Kirsty?
On the table, why I can't look up?
Yeah, why can't we look up 120 on the table? What do we look up on the table?
Z-scores.
Z-scores. That's not a Z-score. think of this as the x-axis now. We labeled it z before because we were starting with 0 and counting by ones, but now we're talking about x's, where x's are IQ scores. But Brian says we need z-scores, which is why I reminded you of that formula we saw before. Could we find the z-score that goes with 120? We could do that. Z equals 120 is the x they're asking about. Minus 100 divided by our 15. You get 20 over 15, 1.33.
Which is 90.9082.
You already looked it up? Let me draw my picture before I look it up though. Everyone okay with I'm getting the z-score there? If I draw a picture for this z-score, that's why I have two pictures. So this is the picture on your left. I'm now going to do the picture on the right. If I'm talking about z's, how do I label this? What goes in the middle? 0. And I'm counting by ones. Oops. Counting by ones.
Is this the table or the graph that's on the right?
The one that's on the right. So this is the one on the left with the original question, and this is the one on the right.
So that one's the same.
So it's important that you recognize that the one here on the left are x values, which are IQ scores in this case. But they could be anything. They could be weights, they could be heights, they could be whatever we're talking about that's normally distributed. But over here, these are just z-scores. But we said that this 120 was the same as a z of 1.33. Where's 1.33 on here? Roughly right here, right? Here's 1.33. And if I want everything to the left of that, tell me how these pictures compare. Yeah, they look like exactly the same area, don't they? From here over, and from my picture over there is a little bit taller because I drew it by hand, but you guys have the ones on your paper, they should have exactly the same area. We're looking for this area, but do we agree that's the same area? Can we find this one on our table? Same area as this guy over here. I don't want to draw the line all the way up. How could I do that one on my table? Look up 1.33.
We can go to the 3.
Yeah, go down 1.3 and over to the 03 column. If we look it up on our table, what do we find?
0.9082.
9082, she says. I haven't looked it up. Does anyone agree with her?
Yeah.
Yes, I hear lots of yeses and see some nods. We're going down to 1.3 over to the 0.03 column. How can we do it on our calculator? How can we do the same problem on our calculator? This one. We'll review.
Normal CDS?
Normal CDF. Normal CDF is what gives us our probabilities. And normal CDF needs 4 things.
Crazy number.
It needs the lower number and then the upper number. And the lower and the upper are referring to the shaded region. So we're shading from here all the way out here forever. The little dot keeps going way out there forever. So Christiana said we put in like a negative 9999, a really big negative number. Because you can't really go forever. We can't put in negative infinity. So we put in a really big negative number because this goes out there forever. That's the number on the left. What's the number on the right? 1.33, this is where we're stopping. Where we're starting, where we're stopping, always left to right. And then our mean and our standard deviation.
Why wouldn't it change, like, why wouldn't it?
Because this has a mean of 0 and a standard deviation of 1. We're gonna go back and do this one, which is I think maybe what you're asking, so maybe hold that thought. What's this give us? Yes, ma'am.
How do you know if you should use the inverse norm or the normal CDF?
Good question. Anyone want to try to answer that for her? When do you use inverse norm? When do you do normal CDF? Go ahead.
If you're given the
Yeah, no,
percentile, and then just, I don't know, you subtract the percentile from like 100.
Okay, so she started with if you're given the percent, you're looking for the z-score, that's when we do inverse norm. So in this problem, we were given the percent, we knew the area, we knew the probability, but we didn't know what the z was. So that was inverse norm. In this problem, we were given the z, but we were looking for the probability. I saw another hand. Was that you, Kirsty, or were you just trying to help out?
Mr. Hubbard told me this is pretty much the same thing. If you're given the percent, use inverse. If given the z, use CDF.
Exactly. The other thing to do is look over on page 1 of your packet here. Page 1, if I could get to the right page myself. The bottom of the middle column on page 1, remember you get to use this on your exam. The bottom of the middle column talks about the normal distribution. It talks about standard normal with the mean of 0 and standard deviation of 1. But the best thing is the very 2 bottom lines there. The 2 bottom lines. We use normal CDF, it calculates probabilities. And then we do critical values, we do inverse norm. Yes, ma'am?
So what should be the negative 99999?
We had to pick some number way off to the left, because this number line goes forever. So we just picked a really big negative number off the end of our chart. You could have picked another big negative number, just that this just goes forever.
Right.
So we just tried to get way off the edge somewhere. It's kind of your choice of how big you want to go. You can put a whole bunch more 9s. I just kind of start typing or writing as many as I feel like. Because you can't go to negative infinity. See the important detail there at the bottom of that middle column there? It tells you when to do inverse norm and when to do normal CDF, in case you forget. What was the answer to this one? When we did it on our calculator? Was it exactly the same? Yeah? Sometimes, remember, it's off a little bit because of rounding. Now, let me show you the really cool thing. Oh, before I show you the cool thing, let me make sure everyone's with me. This was the original question. And we said, well, we don't know how to put 120 into our table, so we have to change it to a z-score. So we changed 120 into a z-score and drew a new picture and said, okay, now we got z's, we know what to do now. We can either use our table or use our normal CDF to get the same probability. Which means we've shaded roughly 90% of the area. 0.90, 91 if we round, right? Which means the answer over here is the same answer. Why is it the same answer?
You change it to a percent?
The area is the probability. We found the probability in the area over here. And what did we say that one was compared to this one?
Same.
The same. So if you ever are asking for help when you're online, the book will always say make sure you change it to a z-score and use the table. But remember, we don't always have to use the table, we could use our calculators. We didn't even need to change it to a z-score. We could have said, oh, we want a probability, let's just do normal CDF. Normal CDF with, lost my blue, everything from here over. What would I put into my calculator for this? What number is way on the left here?
999.
You could, if she wants to use 0, it is way off here. I still would use negative 9999, just something way to the left off the chart. 0 is technically pretty far out there past 55 though, but I would still use negative 9999. And where am I stopping?
120.
120.
And 0 and 1.
Ah, wait, careful.
Oh, 115.
The mean in this case was 100, and the standard deviation was 15. Okay with my 4 numbers? What's the answer here? 0.9. What are the rest of the digits?
0, 8, if you round it, it's 8,
9088 if we round?
8.
Not the same answer. Not exactly the same. Why? By the way, your computer and the MyStatLab will accept either one. Why aren't they the same answer?
Didn't you say that it would vary? Because these have been like rounded off.
So the table sometimes varies from the calculator in general, but there's something that we did to make it be off by a little bit. Something that we did right here. But we got this 1.33.
We rounded.
It was actually, we rounded, it was actually 1.33333. So we rounded our z, which changes this picture just a little tiny bit. Over here, we didn't have to do any rounding. We just put the original numbers in. So this is one where if you went to look it up on, the back of the book if you're practicing, it'll say the answer is 9082 or 9088 if you use technology. Either answer, okay. Which one do you like better?
The second one.
Second one, it's just really quick, straight, quick, sweet, nothing else to do, right? That's all you had to do. Some people will even do this without a picture. Those of you who were in the lab last week, me and everybody else in the lab was like, where's your picture? Where's your picture? Drawing the picture helps you see the left and the right and so forth. Well, see how we just put that straight into our calculator? There's really nothing different, except you have a different mean standard deviation now. So let's do B. What percent of adults have IQ scores above 140? So my picture should be the same every time for this scenario. 100 is the mean, I'm counting by 15s. I'm not even gonna label over here, why not? Besides the fact that I'm lazy.
You're looking above.
Yeah, we're looking above 140, so it doesn't really matter what's going on over here. I'm looking for where 140 is. 140 is way over here. And I want above 140, so higher than 140 is this way. They asked for what percent? Is that different than what we've been doing?
Don't you just multiply the score by 100?
Yeah, just take your probability and turn it into a percent. So if it ends up to be 0.10, then that's 10%. Or if it's 0.15, that's 15%. So they just want you to still find probability, then change it to a percent. How am I going to find probability in this case? Normal CDF. What's the number on the left and the number on the right? Be careful. This region right here only. This is the left, and way out there is the right. 140 is on the left. Do we agree? I'm starting at 140 on the left, and I'm stopping
At 999.
some really big positive number, 9999. This time it's a positive one. And then I'm putting in 115. It saves me from having to draw the picture twice, convert it to a z-score, and then do the same thing I was going to do anyhow. What is the answer? 0038? Yes? It's not the answer they asked for, though. This is the probability. They asked for what percent?
0.38%.
So I have to either multiply by 100 or move the decimal over 2 places. So it's 0.38%. Does that seem about right with my picture? Why? Why does that seem right? It's a little tiny teeny piece over here to the right. If it's teeny, it should be a really tiny percent.
You're saying 38%?
0.38%, so like
Okay,
less than half of 1%. So it's teeny tiny, less than half of 1%. 38% would be a lot bigger, right? 38% would have been like over here more.
Say we got a problem.
Yeah, exactly. And so that's what you want to look at. If it was 38%, something's wrong. But it already was 0.0038, so it's less than 1% for sure. Questions? Okay, here's what I want to do. I'm going to pass back your exams now. After our break, we will do the last 2 examples on this example 1 here, and then continue with more of the same. Before I give you your exams, are we all okay with what we're doing here? Okay, let's get your exams, then we'll take a break until it'll be 2 o'clock on that clock. I'll put the results up on the board too.
Would you guys mind doing a circle?
So we left off, we did example 1B on page 76. If you could put your exams away now, and we'll look at them later. We're going to do 1C. I think you can do it without me. Example 1C on page 76. Try to draw the picture. Start with that. Page 76, 1C. First off, can you draw the picture? You got it, Brian?
I was thinking, sorry.
No, you're allowed to think. I like it when people think around here. Actually, you sat there like you were done, like, I got this, so you're allowed to think though. You got it, Hector? Hector's got it? The question was the probability between 95 and 105. First off, did you label your number line to go with the IQ scores?
Could you use normal CDF?
Yes, we could do normal CDF.
Put 95 and,
So he's already doing it without the picture, or maybe you already do the picture, I don't know.
but just for a little visual, yeah.
A little visual. So 95 is roughly here. 95 to 105? 105 is here. And if it's between those, what does my picture look like if it's between those? It's shaded in between, just give me nice little hand signals here. So from 95 to 105, this shaded area right there. And so what were you saying, Kevin?
Yeah,
Tell me what you were doing.
yeah, I put 95, then 105, then 115. We got .261.
95, 105, 115 is what he said.
It's
And tell me the answer while you were at it. Point 261.
261.
12? Rounding carefully. 2612. Okay. So let's talk about what he was doing.
It's 2611.
It is 1-1?
Yeah, because there's a number one and then
Whoever
a
rounded
seven.
to a 2, you just got outvoted very vehemently. Angry crowd, I tell you. Okay, 1-1. Okay, I believe you. It's not like me not knowing about the quiz this morning. Somebody tell me what Kevin did. And is he right? Okay, she says he's right.
Yeah, because you've got the,
You use that lower.
wait, don't you have it off the, is it high to low?
What were you saying, Evelyn? Kirsty wants to know if it's high to low. What were you saying, Evelyn?
Because you put the lower and then the upper number, right?
The lower and then the upper, right? That's the kind of the question. Remember, if you forget, it's on here in the bottom middle column on the front page. If you're doing normal CDF, it says L, R. What does that refer to? Left and right. Left and right is lower and upper. Left and right. Always left to right. Yes, sir?
I use a chart, so I got a different answer.
It should be close though.
Yeah, it's 0.2586.
2586? That might be off by quite a bit. We'll have to check with the chart. Oh, look, we have 2 rounding. You're probably okay because we have to round 2 different numbers, so you're probably right. You have to round it twice.
Let me go back.
So everyone okay to the left and the right? And then the mean and standard deviation. Does the picture appear to be right? Does this number match this picture? Roughly? How do we decide that?
It's a little over a fourth.
A little over a fourth is shaded. What did you say, Evelyn?
It looks like 26.
Yeah, it looks like about 26%, which is a little bit more than a quarter, right? So you just kind of want to visualize this and seem to be about right. If you had done something wrong and this turned out to be 83% and you had this picture, you should be worried. It's like there's no way that's 83%. 83% is a big chunk of it. That's not a big chunk. Okay, so that's the answer to part C. Good?
Yay.
Not much. Yay! Little celebration. Nice job. D's a little bit different. There's not much there. What do we do for D?
Isn't Q3 75%?
Evelyn says Q3 is 75%. What about that 75%?
Isn't it, I forgot the term.
It's called a percentile or a quartile.
Yeah.
And what about the 75%? Like where would it go on my picture here?
3/4 of it?
3/4, higher, lower,
Below.
below. Remember that from percentiles? A percentile was that percent or lower. So a quartile would be that percent or lower. The third quartile, again, I'm just putting the same numbers up here again, because we're still talking about IQ scores. The third quartile is the same as P75, which means 75% are below our answer. Roughly, where would you guess? 75% are below. You have to guess.
Do inverse norm.
We have to do inverse norm, you're right. But maybe like over here. Roughly right here. I don't know exactly what the answer is. But we want 75% of the area, 3/4 of the area to the left. And so Kevin was saying we need to do inverse norm. Why do we need to do inverse norm? Because we have the percent, and we don't know, in this case it's an X, not a Z. We don't have the X that goes with it. That's the question mark. What is this X right there? What is that IQ score right there? So what do I put into inverse norm? 0.75, that's the area to the left.
0 and 1.
Ah, not 0 and 1, careful.
Oh, 150.
Tricked you again, that's twice I got you.
150.
Yeah, that's what happens, is you get so used to doing 0 and 1 from standard normal, but in this case the IQ scores have a mean of 100 and a standard deviation of 15. Now the good news is, if Kirsty had actually typed in 0 and 1, she would have got an answer like 1 point something. Like, there's no way that's 1 point something. My answer should be somewhere in the hundreds, 100 and something, so that would have probably given you a hint that it doesn't make sense. But when we do that on our calculator, what does it give us?
110.1.
11, yeah.
110 point something?
11, 110.11.
110.11?
Oh, no, it's 12.
Oh, here we go fighting again. Point 12, we agree this time on the 12?
Yeah.
Yes.
I know when you do points and fives that are major, then I know this when you know.
The area. This area, the shaded area, is what you put in the inverse norm. Negative 9999 could not be the area because it's not a probability. Probabilities go into your inverse norm. Does that 110.12 make sense? Look where it is on my number line, between 100 and 115. Yeah, that's a pretty good guess, actually. So roughly right about there, 75% of people have IQ scores that are lower than 110. They probably would want you to round this to the nearest whole number. I don't think they do half points for IQs, I don't know. So, an IQ score of 110 is the Q3. 75% of people have an IQ score less than that. Good? Q3 is fancy for P75, which is fancy for what number cuts off 75% below. All right. So let's turn the page where we have a few more words, but really the same kinds of questions. The note at the top just tells you how you can use your calculator to do what I've already shown you. The left, the right, the mean, the standard deviation, the inverse norm, and the normal CDF. You see that little bold stuff at the very top? Is what we've already been doing. So example 2, now we're designing aircraft seats. It's a little more interesting here. So we've got aircraft engineers. They want to design seats in commercial aircraft so that they're wide enough to fit 99% of all males. That's what they want. Men have hip breadths, which is the width of their hips, that are normally distributed with a mean of 14.4 inches and a standard deviation of 1.0 inches. How wide should the seats be to accommodate 99% of all males? A lot going on there. What do you think we should do? We're going to need inverse norm. Why do you think we need inverse norm? They gave us the percent, the 99%. So that's our hint that we're going to need inverse norm.
We have to draw a picture.
I want to draw a picture first so I know what the heck I'm looking for. So I'm going to draw the picture. And how am I going to label this picture? What goes in the middle? Oops, I put 1. 14.4?
They each go up or down by 1.0.
Because that's the mean. And then we're counting by 1.0. So this would be 15.4, 16.4, 17.4. And if we subtract, you have to spend a little bit of time just filling in your number line. And the question is, how wide should these seats be to accommodate 99% of all males? Where would you estimate that we're going to be on this number line to accommodate 99% of all males?
The tail.
Close to 17.
Way out here? Because what are we saying about that 99%?
Everything.
Yeah, how do we know it's lower? They didn't say lower in this problem though.
It's in the middle.
What'd you say?
So like you gotta like do on both sides, like cost on both sides.
You don't actually have to do both sides. Because when it says the seats will accommodate people, who's gonna, let's say the answer is 17. If the answer is 17, who's gonna fit in that seat?
People with a 17-inch.
17 and lower.
17 or lower. Anybody who's 17 or skinnier, right? So 17 or below will fit there. So the below is actually implied here by saying they will fit, means that they are less than that 17. I don't know if the answer is 17. We're going to find out here. But there's some number right here, some x, where x in this case is a hip breadth. I can't even say that word. Bless you. There's a little tail over here, but what would they give us? 0.99, and that's everybody below. Anybody skinnier than that will fit. Everyone see how the below was implied in that problem? So again, they're saying, what's the x right here that goes with 99% below? We have the area, we have the probability, so we're going to use inverse norm. And we're going to tell inverse norm 0.99, 14.4, and 1. Your area to the left, your mean, and your standard deviation. What'd you say, 16 point what?
16.773.
16.73 inches? What does that mean in terms of these airplanes?
Accommodating.
No, the
Yeah.
seats are gonna accommodate anyone with a 16.73 hip breadth.
Yeah, if they make the seats 16.73 inches wide, which is pretty narrow if you ask me. And let's talk about women who tend to be in general wider than men, but anyhow. If they make them 16.73 inches wide, 99% of all males will be able to fit in them. There'll be some who don't, but 99% of males will. That's what's telling you how wide they should make them to fit 99% of men. This is actually an application of statistics in real life. They have to decide how big or how small can we make these to fit the most people we can in these airplanes, but still be able to accommodate as many people as we can. I mean, because they can make them 5 inches wide and tell everybody, sorry, you don't fit, go home, but that's not the best business policy, right? So they have to decide statistically, where's that cutoff so they can fit enough of the people. Okay with that one?
Yeah.
Okay, let's do the next one. The next one is, now we are in Norway, worrying about these birth weights of these babies. And the babies in Norway have weights that are normally distributed with a mean of 3,570 grams. Use the metric system over there. And a standard deviation of 500 grams. I think actually hospitals use metric system for babies anyhow, because they're more precise. The Ullevål University Hospital in Oslo requires special treatment for newborn babies weighing less than 2,700 grams. What is the percentage of newborn babies requiring special treatment? There you go. Draw a picture. I like it. You guys draw the picture first, then we'll worry about what they're asking next. So we're talking about babies' weights. What goes in the middle? 3570. The mean always goes in the middle. And then we're adding and subtracting
500 grams.
500. So this will be 4,070, 4,570, 5,070. I'm adding 500 grams going that way, and subtracting going this way. Counting by 500s. Okay, so I draw the picture. And I need special treatment for babies weighing less than 2,700. What'd you say, Christiana? So it's going to be a normal CDF problem. I want to finish my picture first.
Shade a
Somewhere
little
between
bit
the
above
25 and the 30.
Yeah, 27 is somewhere in here. Here's the 2,700 in there. And which way am I shading?
To the left.
To the left because?
Because we want anything less.
Yeah, the babies weighing less than that are the issue, right? These poor little babies that hardly weigh anything over here. 2,700 or less. These babies all over here. Now the question says what percent? What percentage? What's that asking me to do? Find the probability and then change your answer to a percent. So if we want to find the probability, Christiana a minute ago said that's when we do normal CDF. So you want to find the probability, we have the X, right? We want normal CDF. And we always tell normal CDF what's on the left and what's on the right of this region.
So
What's the
negative
number way out here to the left?
Negative.
Negative 9999, some number off your chart. What's the number on the right? 2700. The mean was 3570. And the standard deviation was 500. What do we get? 0409? Is that what I heard? This is the probability? But the question asked for a percent, so we changed it into a percent, 4.09%. I want to make sure that you are asking me questions. Some of you have been, some of you are quiet. Copying this down is nice, but if you don't know how I knew which numbers to put where, you're not going to be able to do it on your own. So you need to know that you know which numbers go where. Did I answer the whole question, or was there a follow-up? What's the percentage of babies? So 4% of babies require special treatment. So if I'm the director of this hospital, and I'm thinking maybe I should build a new wing for these poor little babies that are underweight. Is there a high enough percentage that I should be worried about that? Should I build a whole new wing for these babies? 4%.
What's the decimal?
It's,
Because it asks for a percent.
Okay, so would it be 0.04?
It was 0.04 was the probability.
Right.
But to turn it into a percent, we multiply by 100 or move it over two places.
Okay.
So is that high enough that we should be worried and we should do something in the hospital?
No.
No, why not?
it's less than 5%.
It's less than 5%. Remember our old definition, less than 5% is unlikely? So it's not very often, not very likely that a baby's going to be born. Some are, 4% of them are that light, but not so many that we should maybe restructure our whole hospital, build an extra wing, hire more staff. We need to be able to accommodate those babies, don't get me wrong. But it's not a big enough problem, we're going to call it a problem, that we should do something different. If it happened to be, you know, say 30% of the time, I'd be a little worried. That's a lot of the babies. That's almost a third of them. So we would have to be, you know, ready and prepared to handle that. The whole reason we learn statistics is so that we can talk about how likely something is to happen and then make decisions on whether or not we should change our business or our practices and whatever we're doing to accommodate those people or things.
So it'd be unlikely.
It's unlikely for a baby to be born that weighs less than 2,700 grams. Do we agree with her? Unlikely? Because it's less than that 5% cutoff. Okay. So let's move on then to what's called the central limit theorem, which is on page 78. The good news is it's the same thing we've been doing. And I think I'm actually going to skip I have this kind of fun activity to show you why the central limit theorem applies. But in the interest of time, knowing that we ran out of time last time, I'm not going to have time to do all that, where I ask everybody to find your like your student ID numbers and talk about what numbers they end in and so forth. But in general, let me just ask you, if I asked everybody to tell me the last number of their student ID number, if I did, do you think there's any number that's more likely than the other ones? Like, are there going to be more zeros than fours? Or sevens are going to be more likely? People are all shaking their heads no. All the numbers are equally likely, right? Whether you have a 0 on the end, or a 1, or a 7, or a 9, all of those are the same. We all agree with that? That'd be a uniform distribution. Uniform, we expect them all to be the same. So if we had done that, if I asked you for all your numbers, we would have had a uniform distribution, straight across. But if I asked you to say, take the average of all your digits, so you have some numbers 0 through 9, you have an 8-digit. We could do phone numbers if you don't remember your student ID number, whatever. If you took the average, do you think you'd get very many zeros? The average of all your digits? Be hard to get 0. How would you get an average of 0?
No,
What did you say?
none of them have that number.
Well, actually, they would all have 0, right? The only way your average would be 0 is if your student ID number was this. If that was your student ID number, you added up all the digits and took the average number would be 0. Where if your student ID number is this, if you added up each of those numbers and divided by 7, the average wouldn't be 0, it'd be something else. So everyone agree that average being 0 would be hard to do? How about an average of 9? If I say the average digit is a 9, how would that have to happen? What would your ID number look like if the average number was a 9? All 9s, right? If that was your student ID number, then your average would be 9. Do we agree that most of us have something somewhere in between 0 and 9, but not that close to 0 or 9? What do you think the average would be? What do you expect it to be?
5, 5, 5, 5.
A lot of 5s, maybe? The average, if you added all your numbers, I think the average number would be a 5.
Like a 4.5.
Or maybe a 4.5. It's actually 4.5. Why is it 4.5?
Because if I had your 0 and 0.
Halfway between 0 and 9, right?
Yeah.
You would expect it to be halfway in between. So the central limit theorem says that even if you have a distribution that's not normal, the mean turns out to be the same regardless when you start taking averages. So if I took, let's just make up a student ID number. I don't want to pick anybody's because then we're all going to go check out their grades and who knows what else. So there's somebody that has a student ID number of 00813446. This particular person. If I find the mean of their digits, of this person's digits, if I add up their digits, and divide by the fact that there's 7 digits there, this is what I'm talking about. If we did that, let's see what it comes up to be. 9, 12. 3 point something. Can someone help me out there?
3.14.
3.14. I just it was 3. Get a calculator. So the mean for this person is 3.14. If I did it for a bunch of people, the more people I did, do we agree that it would be closer and closer to 4.5 just because some numbers are close to 0, some numbers are close to 9, but on average they're all around 4.5, somewhere halfway in between. That's the central limit there. And go back to my example. If we just looked at the last digit, we wouldn't be surprised to have numbers all the way out to 0 and all the way out to 9. But for averages, we would be really surprised if someone said, hey, the average of all of mine is 0. Because the only way you could do it would have been this. Or maybe you had 0.0001 and it rounded to 0. So what happens is your numbers get closer and closer to the middle. They get closer and closer to the middle, and they actually end up acting like they're normal. What happens though is your standard deviation changes when you take a mean. When you look at a mean or an average, standard deviation changes. So let's talk about what I mean down there. The central limit there down at the bottom of the page. If you have any distribution with a mean and standard deviation like we've been talking about, and your sample size is big enough, greater than 30, which is why I made you do 40 for your projects, then the sample means have a distribution that can be approximated by normal. That's good for us because we've been doing normal. With the same mean and this new standard deviation, sigma over the square root of n. That's what I call the new standard deviation. Your book will call it this, sigma with a little x bar down here. Sigma with an x bar, meaning it's the standard deviation for the mean. So let me give you another example of why that's different. If I took everybody in the city of Brentwood. I probably could find somebody who had a salary of, I don't know, $200 an hour. There's probably somebody in Brentwood that has a salary of $200 an hour. We agree with that? Somebody, we could probably find somebody, maybe we'd like to know them, but we could probably find somebody. But if I said, hey, the average salary in Brentwood is $200 an hour? The average? She's over here shaking her head on, no it's not, have you seen my job? The average is so different than one person, right? We could find one person, but to find an average would be really unlikely. So when you start talking about averages, we expect it to be smaller and smaller, less standard deviation, closer to the middle. It might be okay to find one person on an extreme end, but to find an average on an extreme, it doesn't happen. The numbers all get closer and closer together. So down there, that's where the sigma over square root of n comes from. It still works if your sample size is small, if you already have a normal distribution. Otherwise, it's not going to apply in example 3. I will never ask you to find a probability where you cannot apply the central limit theorem. There's a couple questions where it says can you or can't you, and then you just stop. But on an exam, if I ask you to find a probability, the normal distribution will apply. So not to worry that you have to figure out, what do I do if it doesn't? Okay, so let's look at the subtle difference here. Example 5, on top of page 79. Now we're worried about lengths of pregnancies. Pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15 days. The first question is technically a review of what we've been doing. One pregnant woman is randomly selected. Find the probability that her length of pregnancy is less than 260 days. How would I answer that question? I claim that's what we were just doing in the last section.
Draw a picture.
Draw a picture, thank you. Draw a picture. Example 5A, I'm drawing the picture. What am I putting where? 268 is the mean. And then I am doing what? Adding and subtracting 15? 283? 298? Well, I'm adding in my head and borrowing and carrying. 313, is that right?
Yes.
Wait, I have to subtract though, it gets harder. 253? 238? 223?
You put 236 and you said 238.
Oh, see how talented I am? I can say one thing and write another. Here we go. So I've labeled my picture, and the question says, find the probability that her length of pregnancy is less than 260 days. So, what do I want to do?
Normal CDF.
Normal CDF. Can I finish my picture first though?
Oh, sure.
What will my picture look like?
Highlighted from the left down.
To the left of
260.
260. So we have to find the 260, which is roughly here. And everything down, Hector says. We agree it's going down to the left?
Yeah.
Because?
Less
Less than. So now Brian says we want to do normal CDF. To find that probability. What am I going to put into my calculator? The number on the left here is negative 9999. The number on the right is 260. My mean was 268. And my standard deviation was 15. What do we get?
2969.
2969? The follow-up question asked if it's unusual, change that to unlikely. Is it unlikely for a woman to have a pregnancy that lasts less than 260 days?
No.
It's not unlikely for that to happen, because it happens roughly 30% of the time. It's not very unusual for one woman to have a pregnancy that's that short. Okay with that part? Let's really review what we did. Look at the subtle difference in part B. So now you have 25 women who went on a diet, and it says find the probability that 25 selected women have a mean pregnancy length that's less than 260. What? The mean is less than 260. The average of those 25 women is less than 260. So highlight or underline that word mean for sure, because that's the big key here.
Did you use that formula?
That's that formula I was just talking about, yeah.
Whoa.
So in this case, if we wanted to write out the question, this was the probability that one woman had a length less than 260 for an X, right? You agree that was the question that we just did over here? Over here, what are they asking?
For the mean.
The mean is less than 260. The word mean is crucial in that one. So there's two parts to tell you something's different. They're talking about the probability of the mean, and they're telling you they have a group of 25 people. Over here, they just talked about one woman, right? Now they have a group of 25 women. They're giving me an N, a sample size of 25 women. So the two keys are they're asking about the mean and they're giving you an N. When that happens, you have to get the new standard deviation. Other than that, it's the same question. It's much less likely when you take a group. So we have to do the new standard deviation. We take the old standard deviation divided by the square root of n, which in this case, the old standard deviation was, what was it? 15? Divided by the square root of 25. The new standard deviation is 3. What? Which means the averages won't be as far away from what we expected. Just like the guy who makes $200, right? One guy who makes $200, that could happen, but to have the average be that much is just really extreme. So it changes how spread out your numbers are. My picture now looks different. 268 still goes in the middle. But what am I going to count by now? Count by threes. These are now X bars, the mean. I'm going to count by threes now. I can do that easier. 271, 274, 277.
Excuse me.
I'm adding and subtracting 3. So the key that tells you you need to use what's called the central limit theorem is the key that it said their mean is less than 260 and they gave you a sample size. What does my picture look like now? Where's 260? Yeah, way over here now, right? 260 has now moved. And less than 260 is this little tiny tail over here. To the left of 260. Do you agree that just the picture alone, that has a much smaller probability than this one does? How would I find that probability? Normal CDF. Almost the same thing I did right here, except that
It's the opposite. The upper number is negative.
It's still the same region, I'm still going from over here to there.
You just changed the standard deviation.
All I'm doing is changing the standard deviation, right? I'm still going from negative 999 to 260. I still have the same mean. The only thing that's different is my standard deviation. I'm gonna write it up higher because it's gonna be too low for some of you in the back there. So it's normal CDF, negative 9999, 260, 268, and 3. This is the only thing that's different. There's a 10-point problem on the next exam where I ask you this question almost identically. I mean, it'll be a different situation. But it's just making sure that you recognize that you need to use that new standard deviation. What's the answer here?
0038.
0038? That's a very tiny probability. It's really unlikely for a group of 25 women to have an average that low. It's not unlikely for one woman. We talked about that over here. One woman, it's not surprising. Happens 30% of the time. But to have an average that low, extremely unlikely. This is really unlikely to happen. So look at the question there. Part C. If 25 women do have a mean less than 260, so something's really unlikely, but then it happens, does it appear that the diet had an effect? These 25 women all went on the same diet, and then they all had an average pregnancy less than 260, something that we know is unlikely to happen. What would you say? I got a couple people nodding. Let me word it again. If 25 women go on a diet that doesn't affect them, the chances that their pregnancy lasts less than 260 days on average is 0.0038. Extremely unlikely, almost zero. It's almost impossible to have a group of 25 women have a pregnancy that's that short on average. So if their diet didn't affect them, it's almost impossible to happen. But it did happen. So what do we think? The diet must have affected them. We don't know for sure that it did. That's going to be some more research, obviously. But that's the whole point of statistics. We assume that the diet doesn't affect them. And then we say, well, how likely is this to happen? Extremely unlikely. Oh, then maybe our assumption was wrong. Kind of going back to, I don't remember how long ago it was now. If I assume I have a fair coin, but I flip it 100 times and get 99 tails, we're not going to assume it's fair anymore. Because that's so unlikely to happen. So we're going to assume that these women are all fine on this diet, but something happened to them that was so unlikely that we're thinking that maybe the diet did have an effect on them. So the answer to part C is, yes, it appears that it has an effect and the medical supervisor should be concerned. Something happened that we know statistically was really unlikely to happen. What if one woman has a pregnancy less than 260? Are we worried? If one woman does? No, that's 30% chance that could happen just randomly, right? It's no big deal. 30% of the time that happens for one woman. But as soon as you had that group that had an average, now we're concerned because it's so unlikely to happen for the group. Okay, let's do one more of this. Now we're going schemes. Page 80, last example here. And in the interest of time, I'm going to skip example A and just do B. Let's talk about the difference in them and why I can skip A. Read question A and question B. I'll give you a minute to read the top and read those two. Page 80.
Is it working with the same numbers?
I couldn't hear you say.
Is it because we're finding the greater, the weight greater than 167 in both of them?
So they're both doing a greater than 167. Both part A and part B are asking the same question. But what's the other difference in part A and part B? B is talking about the mean. See how part B says that the 12 men will have a mean greater than 167? So it's similar to what we just did with these pregnancies. We could talk about one woman, but what about the group of 12 or 15 women or 25 women we had over here? Sorry. So in part A of this problem, which I'm going to skip because we're going to run out of time if I don't, do I need a new standard deviation
Yes.
in part A?
No.
No.
Part A I don't, right, because it's just one man.
B.
But part B, we will need a new standard deviation. And what are the two key things in that problem that tell me I need a new standard deviation?
The mean.
The word mean
12 random.
and the 12 men, exactly. The fact that I have 12 men and they're talking about a mean. And I'm going to do this one without even drawing the whole picture. See if we can handle that. Watch me live on the edge in the last 3 minutes. What's the mean?
172.
172. Men's have weights, it's up at the top there. Men's have weights of 172 and standard deviations of 29. But in this particular case, because I'm doing X bar, my new standard deviation is going to be
29 over 12 square root.
29 over square root of 12. The sigma over the square root of n? Not a nice number like last time. Someone help me out, give me a decimal here.
8.372.
8.372? I'll say 8.37. Someone agree with Ariana?
Yep.
Okay, so I have that. I have my 172. The question is, what's the probability that these 12 men will have a mean greater than 167? 167 is over here somewhere. To the left of 172, right? I'm not labeling the whole thing, I'm just gonna get an idea. Just finding where 167 is. Greater than means what? To the right. I want to find that probability. So what am I going to do?
Find the less than and then subtract it from there.
Actually, with our calculator, we just have to tell it the number on the left and the number on the right.
Oh, okay.
You could do that, but we don't need
Or
to.
it'd be 167.
167's on the left.
9999.
Some really big positive number on the right.
And then,
The mean, which was 172. And watch what I'm going to type in right here. When you're going to do this in your homework, you can actually type it in just like we have it written up there. You don't have to first find it and then put it in there. You can type it in exactly like this if you want. 29 divided by square root of 12. You can put in 8.37 if you want, but that got rounded. You can type it in just like this. 0.5,
68.
568. So I know we're out of time, but the question was, this is how the gondola would be over its maximum weight. So there's about a 57% chance it's overweight. You want to get on?
no way.
No way. Yes.
I don't know if you know.
So what'd you put?
Yeah.
Different answer? Uh-oh.
I did.
Uh-oh, you just got outvoted. I don't know who got me the 568. What's the other answer?
724.
I got two.
Someone tell me, starting from beginning. Point
7248.
7248?
That's what I got.
Uh-oh, 7249? Is that what you got, Christiana?
I got 4.9.
It's either 48 or 49 based on whether or not you rounded here. I'm not worried about that. If you did this one or this one, you'll get a slightly different answer. It's either 8 or 9, depending on if you did this or you did that. Either way, it's more than 50, now it's a 72% chance it's overloaded. I don't wanna get on, they should do something about it. I'll see you guys next time. If you didn't get this number, let me know. I don't remember who gave me the first one. Brian, was that you?